Hi everyone, welcome to week 8. We're looking at exponentials and logs this week. We'll get going in just a couple minutes time. Welcome to week 8. I hope you're all safe and well. So, we're looking at exponentials and logarithms today. As always, we're going to run through and look at the rules and then look at some of the applications that we've got going on. Live chat and messaging available to anyone who needs any help. As always, pause the video if need be. If you're still working on a question and we start going through the answers already, pause the video. And more problems in description and feedback always welcome. So, I'm going to turn my camera off. So these are the things we're going to look at. There's only 4 bullet points here, but actually this is quite a heavy topic and there's a lot of parts to it. We really want to make sure that before we start working on this, we've got a really solid grasp of algebra and coordinate geometry, so make sure you've watched those 2 lectures if you haven't done so already. But let's get going. So I'll give you a second just to make a note of this and get it copied out. Hi Breathe, good to have you. So this is how logarithms work. Logarithms allow us to find out powers. So for example, if we had 10 squared equals 100, which we know is true, obviously, we could rewrite this as log base 10 of 100 equals 2, right? What logarithm is saying is what power would we raise the base number 2 in order to get the number that we are applying the logarithm to. So if we apply this power 2 to the 10, it would get us to 100. Right? So that's what logarithms are saying. So let's just have a go and make sure we're really comfortable going through and switching between logarithmic form and index form. So I'm going to just write that example back up again. We had 10 squared is equal to 100. And we've got log base 10 of 100 equals 2. So I'll give you some minutes now just to go through and answer these 5 questions here. and then we'll go for the answers in about a minute's time. So I'm just going to start writing up these answers to the first few ones. Remember, what we said, the way we describe it is, what power of my base number will give me the value of what I'm logging. So that's the first one up there. So C is slightly more complex because we've got an algebraic term and it's not as easy to conceptualize. But we should still understand that we've got A is our base number, so that's what becomes the base of the log. And we're taking the log of 8. Part D, we need to treat this exactly the same way we did previously and make sure that we turn these around. So rather than 64 equals 8 squared, we've got 8 squared equals 64, but the principle is still the same. And then lastly for part E, so again, we've got our base number here, our power, and the thing that we are logging here. So this is log base x of 10 equals our power. Okay, so you should see that out throughout all of those. The common thing is how we're using our base numbers, and our index is always our outcome. So now we're going the other way. You just want to pay attention to the vocabulary here. This word evaluate means give a value for. So we don't just want to write this in index form, we want to give a value for these things. All of these things should have values. And what we're asking is, what power of 7, in this first one, what power of 7 will give us 49? Just going to be 2, because 7 squared obviously equals 49. So I'll give you a few more minutes just to go through and complete the rest before we go through those answers. So again, part B, you're asking what power of 2 will give us 32. So our answer here So I'm just going to start going through these last 3 answers now. Again, what power of 4 will give us 1? Well, we know anything to the power of 0 is 1. Question D, I'm going to rewrite slightly differently, and I'm going to put this, the 1 over 2, as into index format. So we're going to use the power of -1 there, 2 to the power of -1. This makes it actually a bit more straightforward. What power of 2 gives us 2 to the power of -1? Well, obviously it's going to be -1, right? This is already inside the log here, it's already in index format. This is like saying above question A, if you had what log 7 of 7 squared, or for part B, log 2 of 2 to the 5. And then we see this in part E as well. What power of x will give us x cubed? The answer is 3, right? X to the power of 3 will give us x cubed. This is what we're saying. Okay, so I'll give you a second just to get this copied out, and then we're going to look at go on some other bits. But this is really important to understand this relationship between a to the x equals b, and then how that relates to the log format of log base a of b equals x. And to be able to switch back and forth between those two things as well. So, next some retrieval practice. Just try and retrieve as many log laws as you can think of. As many log laws as you can think of. I'm going to give you a few hints now just in case. So how can we simplify these 3 statements? So the first one, we can combine this to give us log AB. And using the same idea, we're going to combine this to give us log A divided by log B. This last one will give us log A to the power of x. It's really crucial to understand that it's A to the power of x, not the whole function, just A to the power of x. the last thing to note is that if we have log with no base number given, this is assumed to be log base 10. Okay, our number system is in is a decimal multiple system, number system, sorry. So it goes out, it works in powers of 10. This is why if there's no number given here, no number specified here, we assume that it's 10, and we're safe to assume that. Okay? So we've got these laws here. So, using those laws, let's have a go at trying to combine these logarithms here. We're trying to simplify them. If you finish with those questions, there's some more on your right hand side here. We're doing the opposite. So I'm going to go through this first one on the left hand side, just to start off with. We said we can combine these to make log, which is going to be log 21. We could actually go straight to this final answer here. I'm just showing you explicitly what's involved and how we get that 21 and how we're combining those logs using the laws that we discussed earlier. So I'm just going to start writing up these answers for the left hand side. And crucially, let's look at the difference in language here. We don't have the word evaluate in either of these questions. We don't have the word evaluate. It's saying express these as a single logarithm or express these in terms of separate logs. And that wording is crucial. We don't want to work out the value of log 64. We just want log 64. Underneath. So we've got parts A, B and C done there. And then part D, there's a number of things we have to do here before we can combine them. So the first thing is to bring all of the coefficients of the log up and make them powers of the number. Then we want to find out these powers. And then lastly, we want to combine them and bring them all together. So this would be the log of 125 multiplied by 1296 divided by 1000, which leaves us with this as our final answer there. Okay. So we've got those answers to the left hand side there. I'm going to give you a few more minutes just to go through and get the answers for the right hand side done also. Josh, yes, for part D, really good question. We must do it in the order that we've done here. So we're going to do the 125 multiplied by the 1296 first before we do that divide by 1000. Really good question there, really good question. And that is because we just do it in the order it's presented. And then let's start going through the question on the right hand side. So first we're going to split this up and separate out the multiple. Then bring this power down. We just want it in terms of log a, not log a cubed. So we get that. You're welcome, Josh, no worries at all. And then part B. Again, similar thing. We need to split up the logs here first. See, now we're starting to get a bit more complicated. This is where the idea of Josh, what he's mentioned earlier about the order of operations becomes really important. So let's really take our time to split this up. We're going to split this as log AB squared minus log C cubed. Then we'll split up the log AB and then our final step, we'll bring these powers down and make them coefficients. So we get this as our final answer there. And then lastly, log D will follow a similar kind of idea as, sorry, not log D, question D will follow a similar pattern to question C. So again, let's split up and get rid of the denominator first. So you get log of root C, and actually what we want to do as well is change this root C into index format. So this is going to give us log a to the 4 plus minus log C to the half. Once going back to topic 1, understanding that root is to the power of 1/2. And then just like the final step in part C, just bring our powers down and make them coefficients. And we've got our solution at the bottom there. So I'll give you a second just to get that copied out. Before we go on. Okay. So half an hour, we've gone through quite a bit already. Let's look at what we're going to next. So we've got some exam style questions here. And I'll give you a moment just to answer those questions. And I'll reveal this question at the bottom in a few moments' time as well. And remember, as we're going through this, the question we're asking is what power do we need to raise our base number to in order to get the thing that we are trying to log? And I'm just going to go ahead and show you this question at the bottom as well now. So I'm going to start going through the answers to this top question here. And we should get, because anything to the power of 0 is 1. So it doesn't matter what a is, we know a is bigger than 0, and therefore the value of log a of 1 is going to be 0, because the power that we would raise a to is 0. For B and C, what we want to do before we find the value of these things is simplify them and put them into index format. So a cubed in brackets 6, again going back to topic 1, looking at the laws of indices, when we have brackets like this, we're going to multiply our indices. So this is going to become a to the power of 18, and log base a of a to the 18. Again, we're asking what power do we have to raise a to in order to get a to the 18? It's just 18. The other way of thinking about it is that logarithms and powers are inverse functions, just like times and divide. So having log a will cancel this power, so all we're left with is our index as a number rather than a power. And again, lastly, part C, this is log a of a to the power of a half. So our final answer is just 1/2. Then I'll give you a few more moments just to go through the bottom question there. Again, think about what log you need to use for this question. So I think there may be some issues going on with the buffering. The internet seems to be playing up today. So if there are any issues, please bear with, and we will make sure we come back on as soon as possible. So just another couple moments, and then we will go through the answers to this bottom question. So part A, First thing we want to do here is split this up. So we've got log 3 of 9 plus log base 3 of x. And then log base 3 of 9 is going to be 2, because we need to raise 3 to the power of 2 in order to get 9. It already tells us that log 3 of x is a, so this becomes 2 plus a. And then part B will follow a similar pattern. First we split up these logs using the log laws. To get this. And then for the first part, log 3 x to the 5, we want to bring the 5 down to make it a coefficient. So we get that. And log base 3 of 81 is 4. And then again, we know that this is a, so actually our final answer is 5a plus 4. And then this last question then, we want to substitute the answers we've worked out in parts A and B into part C. So this is going to come, well, this we know is 2 plus a here. And this part here is 5a plus 4. So we're going to get 2 plus a plus 5a plus 4 is equal to 3. And this is just a straightforward solving in terms of to find a GCSE level. So we'll get 6a plus 6 equals 3, 6a is equal to 'So we get this as a value for a, but crucially, the question has asked us to solve for x. So a really common mistake here would be people would find the value for a, and then they say, well, we found a value for an unknown, and they would stop there. But this is a crucial understanding of why we have to find a value for x. Second hint is, it says give the answer to 4 significant figures. Well, negative a half is too easy to give to 4 significant figures, no rounding involved. So that's another hint that there's something more to this. So we get log 3 of x. We can say therefore log 3 of x is equal to negative 1/2. And now we use that relationship between logs and exponents that we looked at right at the very start. So think about what this would be. So we're going to get something is equal to x. What would we get on the left-hand side there? So this is going to be 3 to the power of minus 1/2. And actually we could start using our knowledge of indices and negative indexes and fractional indices to simplify that. But the question says just find it to 4 significant figures. So the easiest thing is just to plug that straight into your calculator and say, well, therefore x is equal to 0. And then just round it to the appropriate value given in the question, which would be 0.5774. So I'll give you a couple moments just to get that copied out and add anything you need to add to your working before we then go on. Okay, so next bit. So now we're looking at solving equations using logarithms. And in topic 1, we looked at solving indices equations. And it would give us equations something like this on the left-hand side, where we have 2 to the x is equal to 32. And what we would do is change them both into the same base and then equate our indices. So from here we say therefore x equals 5. Or for a slightly more complex one, we'll still use the same idea, and we would get equals 3 to the 4. Therefore 2x plus 1 is equal to 4, and rearrange to find the value for x. We can't do that with numbers that aren't index values of each other. For example, 81 is an index value of 3. But 82, for example, we wouldn't be able to do this because we wouldn't know what power this would give us. And this is where logarithms becomes really useful. Now they allow us to be able to calculate and work this out. So instead, for part A, for this question here, part A, we can say therefore log 2 of 37 is equal to x, right? Similarly to what we've done previously. And we will be able to work that out. But we can also now do that for more complex questions like this as well. So I'm going to give you a second to do this question here, B. And then part C we have to do something slightly different. So part C we have to do something slightly different, and I'll go through that in a moment's time. If you feel like you know what you're doing, feel free to go through and then you can check your answer afterwards once you've gone through it. But have a go at part B and then we'll come back to part C in a few moments' time. So let's just go through part B here now. And again, we're saying for part B that log base 3 of 850 is equal to 2x plus 1. So you can see parts A and B, the left hand side of each of these questions compared to the old method and the new method are exactly the same, but now logarithms allow us to be able to work with these, let's call them difficult numbers, more awkward numbers. So we just type this side into the calculator, log 3 of 850, and we'll get that therefore 2x plus 1 is equal to 6.13, and we leave it unrounded for now. And then I'm going to go through and just solve for x. We get a final answer of 2.56, and we would round it to the appropriate value asked for in the question. So lastly, question C then. This time we have to do something slightly different. What we do here for question C is take logs of both sides and then apply the log laws. So what that looks like is this. We start off with our base question here, and then we're going to say, well, log of 2x plus 1 is equal to log 3 of 3x minus 2. And this is similar to if we were multiplying both sides, dividing both sides. We're just applying a function and operation to both sides of the question. Then we want to use our log laws to bring the index down. So I'll give you a second to do that and then we'll go through and check it. So here we've got x plus 1, and it's really important we have this in brackets here, of log 2 is equal to, again we want this in brackets here, log 3. And then from here, we now need to isolate x and get x by itself. So let's expand these brackets. Remember, log 2 and 2 log 3, they're just numbers. Okay, these are just numbers. Just will scroll this screen up a little bit. These are just numbers. So we rearrange them just as numbers, put all the x's to one side, and all the other values to the other side. And then from here we can now start to isolate, because we can factorize out the x from the left hand side and then continue rearranging to get x by itself. And then we could apply some log laws here and try and simplify this, but ultimately it's going to go into a calculator anyway, so I'm just going to keep it as it is, but divide through so we get x on its own on the left hand side. And we should get that as our fraction there. And then once we plug that into our calculator, we should get x at the value of 1.110 dot dot dot, and then again we just round that to an appropriate value as would be given in the question. Okay, so I'll give you a few moments just to get any of those bits that you need to get copied out. And then we'll look at an exam question that builds off of this topic in this area. So let's have a look at that question then. So I'll just give you some time to have a look at this and go through it, and then we'll go through the answer in a few moments' time. So I'm just going to start this question. But I'm just going to put the working up. I won't talk through the explanation, so you can continue to focus if you're still working. So now we're on to the final step here. So we get our answer 0.51 81 dot dot dot, and again rounding it to 3 decimal places in this case would give us this as our answer. Okay, so like you can see, these questions are quite similar. The steps involved: take the logs of both sides, expand your brackets, factorize out, and rearrange to find x. So we've got one more question on solving equations. So we'll go through that and then we'll have a very short break. So these last two questions here, I'll go for the top one as an example, and then the bottom one we'll look at as an exam question of a similar ilk. So I'll give you a second just to get the top one copied out and read through it. So this is an unfamiliar question, but actually we can turn it into a fairly familiar one. And all we need to do is say let 3 to the power of x equal y. And then this equation at the top becomes y squared minus 8y equals 0, which is then a very straightforward quadratic. We just factorize this and get our values for y. However, there is an added step we must find. We're solving for x and not for y. So although we've used this substitution of y, we now need to go back and say therefore 3 to the x is equal to 0 and 3 to the x equals 8. Now no power of 3 will give us 0. There are no solutions for this part here. No solutions for that part here. For the right hand side, we then do what we've done previously, which is to take logs. So I'll give you a second just to work through that question and then I'll write up the answer to that one. And if you've done that, then I'll also reveal this question at the bottom here, which you can have a work through. So we should get log base 3 of 8 is equal to x, and therefore x is equal to 1.89 rounded to an appropriate value as asked in the question. Okay, so use that example to help you answer this exam question on the bottom. I'll give you a few minutes to go through that, and then we will go through the solutions and have a break after this. So I'm just going to go through the first part of this question here. Again, this is something we've been doing since the start of today, so I'm going to move that 5 down to the base, take the log of 7, and we get therefore x is going to be 1.209 dot 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 dot. Rounding it to 3 significant figures, we get 1.21. Then part B, again we want to use that substitution. This type of question is really common. So we get this. This is a much easier quadratic to work with. Just going to move this up here. Much easier quadratic to work with. So we can get our values for y. So this should be 12 in here, my apologies. So we get our two values for y here. we already said, well, y is equal to 5 to the x, so therefore 5 to the x equals 5, and 5 to the x equals 7. Well, 5 to the x equals 5 is straightforward, therefore x equals 1, because anything to the power of 1 is just itself. And 5 to the x equals 7, well, we've already worked that out in part A. So for this solution, we get 1.21 to 3 significant figures. Okay, so that equation is now solved. So again, really important, even though we're using that substitution, we must always go back and work out the unknown that is being given in the question. So in this case, it was x. So just before we have it, there's one thing I wanted to go back and clarify and touch on, was question A here. We had a question come in about this question. So I just wanted to go back and be really clear on what this question is. I think some of the wording of the question may be a little confusing. So the question is log base A of 1 when A is greater than 0, and then we've got an answer of 0. Well, let's not use base A. Let's use a number and see if that helps. So if we have, let's say, log 3 of 1, what would that be? Well, like we said, any number to the power of 0 is 1. When that number is greater than 0, any number 3 to the 0 is going to give us 1. So this would be 0 here. Or we could have log 99 of 1. Again, what power of 99 would give us 1? 0. So if we go back to this, again, we're asking what power of A will give us 1? Knowing that A is greater than 0, the answer is this. So it's really important to understand A as a number is greater than 0, but log A of 1 is equal to 0. Log A of 1 is greater than 0. So just separate, make sure it's really clear on the differentiation between the two ideas there. Okay, so I make it 12:11 now. Let's say back at 12:20, and we'll get going again there. I'll see you guys in a bit.
back, everyone. We'll get going in just a minute's time or so. So hope you're ready. Hope you've had something to drink. And we'll get going very soon.
Okay, I make it 1220, so welcome back. And let's get straight into it. So, logarithms and exponentials, like I said earlier, are inverse functions of each other. And so it's really clear that we need to understand how they work. If we were to graph an exponential function, it would look something like this. Right, let's just call this as a generic a to the x. A could be 3, 4, 28, 2009, whatever it is. Some positive value, some positive integer. And this value here would be 1, because like I said, anything to the power of 0 is 1. So when x is 0, a to the 0 will give us 1. And we also know that inverse functions are reflections of each other in the line y equals x. So if that function we've just drawn there, the orange one, is a to the x, an exponential function, then a logarithmic function is going to be a reflection in this line here. So we're going to get it looking something like this. Where again, this is going to have value 1 there. And there's a significant part of this then builds on and to graph transformations, but the graph transformations, similarly with the trig graphs, they all have the same foundation, so we're not going to cover them today. But if you want to have a look at graph transformations, they're in topic 1, but they would have a similar function where if we were to have the function f of x is equal to a to the x, then we would have f of x plus 2 is equal to a to the x plus 2. That would involve a transformation 2 units to the left. Okay, and so the principles behind them are exactly the same as any other graph transformation. So we're going to go on. I'm going to give you a second just to get any notes you want to get copied out there. So next bit. We then also have these ideas called E and ln. E is a natural number. It is just a number like pi. It's irrational. It can't be expressed as a fraction. It's non-repeating and non-recurring. And it's something like 2.718 ... We're not too fast about what it is. It's just a number that occurs very often in maths, in nature, and physics. So it's designated a specific letter. And it represents this value here. ln is then log base e. Rather than writing log e, because it occurs so frequently, it's just been shortened to ln, the natural log. So log base e is ln. But ln and e function in the exact same way as we've previously looked at. So for example, part A, this would just be log e of 7 equals x. But again, we said we don't write log e, so actually this would be ln 7 equals x. And we'll just plug that into our calculator using the ln button. And again, we just go through and find a value for that. Part B, again, we can use the exact same log laws and the relationship between logs and exponentials to work that out. we can rewrite where ln is base e. So what this is saying is e to the power of 4 will give us this thing when we're going switching back to the alternative format. This question is the inverse of what we've done in question A. We've gone from the exponential to the log. Now we're going from the log back to the exponential. So we get this. And then again, we just rearrange and solve to find a value for x. Lastly, part C, very, very similar. In fact, identical to the questions we looked at earlier where we had 3 to the 2x and 5 to the 2x. We use a substitution there. So I'll give you a second just to go through, finish off question B and answer question C, and then I will write up the answers to those. So part B there, we've gone through and written up the rest of the solution. Firstly, rearranging for x and then just plugging into a calculator to find the answer, 18.53, which we then just round to an appropriate value. So again, to solve this question, part C here, we want to say let e to the x equal y. This becomes y squared plus 2y minus 15 equals 0. Simple quadratic to solve. And then we're going to factorize this. So we got 2 values for y. So we've got y equals minus 5 and y equals minus 3, and therefore e to the x also equals those values. But e is a positive number, as e is a positive number, there is no power that we can raise it to that will give us a negative answer. So there are no solutions for this first part here. Josh, I'll finish this question and then I'll come back and answer your one. So we've got e to the x equals 3, and again we're just going to take logs here and say, well, therefore ln 3 is equal to x, which is then x is equal to 1.098, and we just again round to an appropriate. I think there's some more technical difficulties that we are experiencing at the moment. So I think we are back online now. So let me just go through and explain what I wrote up here. I've rewritten ln as log base e. So you've got log base e of 3x minus 1 is equal to 4. And what we're saying is that then this e, the base number, to this power is equal to what is inside our bracket here, right? The base number to the answer is equal to the thing inside the log. That is the relationship of logs. So what we're going to do is rearrange that. Or the other way of thinking about this is, let's apply the exponential to both sides. Let's apply the exponential to both sides. Just like we would multiply both sides, times both sides when solving a question, we can apply the exponential to both sides. And what happens is, because e and log base e are inverse operations, just like multiply and divide are inverse operations, they cancel out. So what we're then left with is 3x minus 1 is equal to e to the 4. And that's where that e to the 4 comes from. Okay? So Josh, I hope that answers your question. If you're still not sure, please do let me know, and I will do my best to try and explain it differently. But it's going back to that relationship we looked at earlier of a to the x equals b, and therefore log base a of b equals x. So it's going back to this relationship. You're most welcome, Josh. No worries at all. So let's look at the next bit: exponential growth and decay. So actually we live in a time right now where this is highly prevalent. COVID is a disease that spreads exponentially. This is a great example of it. So we've got one person that spreads it to 2 people, they spread it to 2 people, and they spread it to 2 people. And so you can see how we increase. And actually these are in orders of 2. If we were to annotate this, we would have 2 to the power of 0, which is 1, then 2 to the 1 for this row. Then you see we've got 1, 2, 3, 4 here, which is 2 to the 2. Then we have 2 to the 8, and so on and so on. So each range in the population is increasing the power of 2 by 1. And that's why it's exponential growth. And if we were to graph this, we would get the exponential graph we looked at earlier, where it's increasing at a increasing rate. So not only is it increasing, it's increasing at an increasing rate. Let me explain the difference. This blue line is increasing at a constant rate, right? The gradient is flat. It is increasing at a constant rate. The orange line is getting bigger, faster and faster. So not only is it increasing, it's also increasing in value at a bigger rate. So the time taken, for example, to get from 0 to 10 is going to be slower than to get from 90 to 100. Even though the gaps between these numbers are exactly the same, this is going to happen much more quickly than this. Okay? And then exponential decay works in the exact opposite fashion. We would have something that looks like this, right? Where we're decreasing at a quicker and quicker rate. So something like nuclear decay. Those who study physics or chemistry, uranium decays exponentially. Okay, it decays exponentially. So the first half will decrease a lot quicker than the next half, and the next half, and so on and so on. And so these are really important when looking at applications of what we just looked at. So what we've looked at is a lot of the rules and techniques and laws involved in exponential logarithms. What they're really big on in the new specification is applications of each of those things. So we're going to look at that now. So I'll give you some time just to read through this question and get it copied out if need be. So let's have a look at this question on the left hand side. Part A, fairly straightforward, it's just a substitution. So it's just a matter of typing this into a calculator. We should get 27.06 ... again rounding to an appropriate value. B is slightly more complex. It's not just as straightforward as just substituting and plugging it into a calculator, but the first step is still that substitution. So let's go ahead and do that. So now we want to first rearrange and just simplify this down a little. If we divide through by the 200, we'll get 1/4 e to the 0.04 t. And then again here we're going to use that, now is where we need to use that idea of logarithms. So what we end up with is ln 1/4 is equal to, and on the right hand side what we're going to say is ln of e to the minus 0.04 t, just to demonstrate the inverse nature of this. Ln and e are inverse functions of each other. E to the power or something, isn't it? Are inverse functions. So this will cancel with this, and actually what we'll be left with is ln of 1/4 is equal to just our index. And then we rearrange this and we can say, well, therefore, t is equal to ln of 1/4 divided by negative 0.04, which gives us 34.65 ... Again, needing to round to an appropriate value. And lastly, part C. Well, the initial value is going to occur when the time is 0, right? T is equal to 0. So if t equals 0, then the whole power here, the whole power of e becomes 0. So we get e to the 0. And like we've discussed earlier, e to the 0 is 1, just like anything to the power of 0 is 1. So we end up with, let's make it really clear, e to the 0. Therefore, m is just equal to 200 grams. And we've got our starting, that's our initial value of m, the mass of the substance. So get anything you need to get copied out, and then I'm just going to reveal this question on the right hand side for you to have a go at. I'll give you a few minutes to go through that, and then we will go through the answers together. So just to make it clear, I'll rewrite the equations just so it's absolutely clear as well. This is P is equal to AE to the minus KT. Thank you for that, Josh. So I'm just going to start writing up the answers to this question now. I'm going to stop this question here and go back to part A. Part A says t is the time measured from the point p is equal to 2000. So when t equals 0, p is equal to 2000. So we get p is equal to a e to the 0. That just goes to 1. And if p is 2000 when t is equal to 0, then a must equal 2000. So that's where that comes from, the ideal initial value. Just like here on the left hand side, for part C we had 200 because this was the initial value when t is equal to 0. Same idea. The value went at the start, or i.e. when t equals 0, is our initial value. So breathe again, hope that makes sense. If it doesn't, let me know. No worries, Breathe, you're welcome. So just look at this bit for part B here. We'll get minus 1/5 ln of 1/4 is equal to k. So this is close to what we want, except we've got a positive fifth here, we've got log 4, ln 4 rather than ln 1/4. So this is we're going to use some of our log laws with this negative here and say, well, actually, we can rewrite this left-hand side so that it becomes 1/5 ln 1/4 to the power of minus 1. We know negative indices are reciprocals. So this is where we now get our answer. 1/5 of ln 4 is equal to k. And then the last bit then is substituting in your values for k and t and a that we've worked out to work out a value for p. So you get to this point, and easiest thing here is just to type it straight into your calculator. And so we should get an answer of 217.6. Again, rounding to an appropriate degree of accuracy. Okay? So exponential growth and decay questions all follow a very similar kind of pattern like the one you've seen here. So I'll give you a second just to get any notes you need to get finished up, and then we'll go on to the next question. We'll try and wrap it up within the next 20 minutes or so. So we'll just go on to the next slide here. I'll give you a second to get that question, read that question and get it written out. Just having a few technical difficulties again at the moment. I'm really sorry, I'm not sure what's going on today and why it's so bad. But hopefully we're back, so hopefully you can see this new slide here now. I'll give you a second just to read through this question and then get it copied out. Okay. So we've got again an inequality here. And again, what we want to do is use logarithms to work out these values here. So let's take logs of both sides. We're going to get log 0.3 to the power of x is less than log 0.02. And then we use our log laws to bring this index down. So we get x log 0.3 is less than log 0.02. And we can say, well, therefore, x is greater than, I'm going to explain this change in sign in a second, greater than log 0.02 divided by log 0.3. This change in sign here, from less than to greater than, is really, really important. We want to draw our attention to it. So give me a second to copy that out and then I'll go through and explain it. The reason this sign changes is going back to when we first learned about inequalities back in GCSEs. When you are multiplying or dividing by a negative value, the sign of the inequality swaps. And log of 0.3 is negative. Log of any number below 1 is negative. So when we divide by 0.3 in this step here, we're dividing by a negative value, so we have to invert that sign and make it face the other way around. So then our final answer we get is that x is greater than 3.249 ... Okay. So give me a second to get the copy out, and then once you had a go at that, let's have a go at answering this question here on the right hand side. And I'm just going to write this equation out so it's really clear. So just whilst you're answering this question, this first part B on the right hand side links back to the questions we looked at on the previous slides. And if you want to wait for part C, you'll need to set up an inequality that you then need to go ahead and solve. So just about another half a minute more, then I'll start going through the answers to that question. So just part C, if you want it, I'll give you a starting point there just to help. Okay, so part B, 150 like we said previously, is the initial value. In this case, the initial number of members of this site. Basically, this is still the initial value, the idea of it being the initial value. Part C, then we said, at what point is our membership greater than 60,000? Well, this is how we work out our membership here. So we're looking at what point does that go above 60,000 there. So we want to go ahead and simplify that first and then go ahead and solve it. I'm just going to start writing up the solution now. What we get here is 2.995. So the week in which the model predicts the number of members first exceeds 60,000 is going to be in week 2, at the end of week 2. So even though this is 2.995 and it will round up to 3, the actual week in which it exceeds it is week 2, right at the end of week 2. Okay, so we've got one last bit to look at. That's logarithmic graphs. So let me give you a second just to get this copied out. And let's just go through this bit by bit. So the first is an example of what we've seen earlier, right? For example, we had p is equal to a, some constant, times e to minus kt. In this case, because with parallels, y is equal to a, b to the x, right? We've got index here, coefficient here, a base number here, and a base number here. And what we can do is use these logarithmic relationships to make linear ones. If we were to take logs of both sides, we would get this. And then if we take it a step further and use the log laws to separate out the right hand side, we would get this. So use the law here to separate a and b to the x. Then when we've got b to the x, we've used the law to bring the x down and make it the coefficient. And here we can now see, I revealed the last bit, the parallels of a straight line. Y is equal to mx plus c. We've got a log a here, which is just a number. So our c value, our y-intercept. And then log b, the coefficient of x, mx, m being the coefficient of x here, the gradient. So we can see these parallels here and here, and how we can go from logarithmic ideas to linear ones. So let's have a look at how that will work. I'll give you a second just to get that copied out, and then we'll have a look at how that will work in practice. So if we go to the next bit, I'll give you a second just to read through that question. Just to make it clear up here, this axis is log base 10 to the y. So what this question is saying is that there is a linear relationship between x and log y. So let's start to form our equation. If we have log y, remember we said if we don't include the base, we can assume it to be base 10. So we have log y is equal to mx plus c. We need to find these m and c values here. Well, c is clearly going to be this value here. And we've got 2 points, and we know from coordinate geometry that the gradient is equal to the change in y over the change in x. So we can actually go ahead and calculate this. Change in y over change in x, so this is going to be 6 over 3, which is 2. So now we can start putting these values into this linear equation we've got down here. So now we get log y is equal to 2x plus 3. So this is the first bit, relating log 10y and x. We've got that bit done. Now we need to the next part and find one that relates x and y. The way we get rid of a log, remember, is we use an exponent. Just like we use a log to get rid of an exponent, we use an exponent to get rid of a log, because it inverse functions. So if we raise everything to the power of 10, as in base number 10, so we make everything as powers of 10, on the left hand side this is going to cancel with the log, so we're just left with y is equal to 10 to the power of 2x plus 3. We can then start separating this right hand side out. This can become 10 squared in brackets to the power of x, right? Because if we multiply indices separated by brackets, so when we have indices separated by brackets, we multiply them. And in order to add indices, we multiply base numbers. So this will be this multiplied by 10 cubed. So what we've done is take this index here and separate it out into 3 different bits, into component parts. So now we just need to put some values to this. And we can say therefore y is equal to 10 cubed is 1000, and then 10 squared is 100, which is to the power of x. And we have our equation relating x and y. It all started from making this linear relationship and using our knowledge of straight lines to make this linear relationship, but we must pay attention to what's on the x and y axes. If this was log y and log x, then this will become log y equals log m log x plus c. So whatever our axes are, that's what we need to label and put into our equation. So I'm going to go ahead and show this question on the right hand side for you to have a go at, and then we'll go through that in a few minutes' time. I'm just going to rewrite this so it's easier to see. So here, what we did was, just like we said we would multiply both sides by a number or subtract both sides when we're doing operations and functions, what we've done is take 10 and apply it to both sides. So we've raised both sides to become powers of 10. So when we've done that because this is the base 10, log base 10 here. If this was log base 4, then these two numbers here would be 4. Because this is 10, we take that 10 and apply it to both sides to make them powers. And then the 10 and the log here will cancel. The power of 10 and log here will cancel, which is how we just get y. What you could do is go straight from this step, sorry, that step to that step. Right, if you want, there's nothing wrong with doing that. Just making it really clear what would allow us to do that. So please let me know if that makes sense or not, and if not, I'll try and explain it again a bit differently. You're welcome, Booth, no worries. So I just want to make sure we're on the right track with this question on the right hand side. And our starting equation, when we're making this and modelling it linearly, should look like this. Just make this a bit clearer. And then now we can substitute from here, substitute our values to find M and C. So we've got a value for M, and therefore we can find our value for C as well. And then we can start forming our equation. So we've got that first part done, again relating log x and log y. Now we need to turn it into just x and y. So think about what we did on the left hand side here to go from log y to y. So we should end up with something like this. We can cancel out on the left hand side the raising as power over 10, and the log will cancel out to leave us with just y. And on the right hand side, I'm going to rewrite this first as log x to the 4 plus 1. And then again, let's separate this out on the right hand side. Just like we did here, we had 10 to the 2x plus 3, and we separated out the 2x. So we had 10 to the 2x times 10 to the 3. Let's do the same thing here. And now what we can see here is, again, we get a situation where raising to the power of 10 will cancel with the log. So we get x to the 4 times 10, and then just tidying it up, we get our final answer, like this. With really good question, my apologies, I glossed over that one. So if this is, we found m as 4, and we've got a point here. Remember, the gradient describes our change in y as we change x by 1. So if I go here, left by 1 to get 0, my y value is going to decrease by 4 because my gradient's 4. So we end up with 1 as our y value. So that's where we get that c value from. So just using the idea of a straight line and applying the gradient to it, to the coordinates on it. Okay, so I'm very aware we've been going for almost 2.5 hours now. Really long haul today. This is a very, very big topic. The last two we've got left will not be this big, so hopefully they'll be much shorter, but we'll go through one more slide just to finish off and cap this off, and then we'll call it a day. You're welcome, Breathe, no worries. So the first thing I would do just on this left-hand question is plot a quick sketch of this graph. What it then allows us to do is, in fact, ignore all of this sentence here. So now we can see this question is very similar to the one we've looked at in the previous slide. Again, in fact, I'm just going to go ahead and review this next one as well, just if you get onto it, and then we'll go through these two questions and we'll call it a day after this. So just to help you a bit with this first question on the left hand side, we should have it in this kind of format to start off with. So just written up the M and C values there and substituted them into the equation that we've got so far. And then it's given the format. It's given us the format of the equation as they want it. Up here, y is equal to kb to the power of x. So I just need to go through and then rearrange this log y equation we've got down here into that format. So I'm going to go through and just write up the finished solution for the left hand side. So we've got our final solution here. I've left it as 10 to the 8 just because it's clearly a big number, so it's easy to leave it as that. And just to make it really clear for the examiner, I'm going to specifically and explicitly write down the values of k and b that we get. Okay, so we get that for the left hand side. I'll give you a few more moments to go through the right hand side, and then we'll go through that question and we'll call it a day after that. Again, make sure you're paying special attention to the labels of the axis on the right hand side and how they've changed from the left hand side. And the impact that will then have on our linear model. Just another minute and then I'll start writing up the answer. As always, if you're still working, feel free to pause the video and then you can unpause it when you finish your answer. Okay, so final question. I'm just going to start working through this and writing up the solution. So our final steps here, we get therefore y is equal to which is simplified and tidied up to give us that as our final answer. Okay. So it's been an absolute marathon today. We have gone on for a significant amount of time. Well done for sticking with it. Really good job for staying focused for such a long period of time. Apologies for the technical difficulties we had and the times we were cutting out. Thank you for sticking with us through that as well. We've got 2 weeks left. Next week we're going to be looking at vectors, and in the final week we'll be looking at proofs. As always, a quick summary here about what we've looked at today. Reminder that logarithms are the inverse of exponents of powers. E is a natural number and ln is a natural log, which has log base e. We can use them to model linear plots and to solve equations as well, and the specific log laws that we looked at too. And lastly, as always, follow us on Twitter, follow us on Facebook. We've got loads of free resources on our website as well. And we will see you 11 AM same time next week Wednesday for topic 9, which is going to be vectors. Take care, everyone. Let's look at that question then. So let's go back to here, and you asked so we said, why do we log the x as well? Remember, when we take logs, we must apply the logs equally to both sides. Just like when we times, we can't times one side and not the other. If we adding, we can't add to one side and not add to the other. So when we apply the logs, when we apply the logs, we look at first, what are we given in our axes? On this left-hand side, the relationship is between log y here and x. So our equation is log y is equal to mx plus c. But on the graph on the right-hand side, the relationship is between log y and log x, which is why our equation here then becomes log y equals m log x plus c. So the log x and log y, or the x and log y, are dictated by what our graph is showing. So let me know if that answers your question. You're welcome, Booth. No worries at all. Take care.